is just, we're a little off on the homework, but so I'm giving you guys the week off. Does mean that there's technically homework due the week of Thanksgiving. There won't be a quiz over it, but it just made more sense with the way that material that we're covering right now and the homework we're working out. So yeah, so I mapped out the rest of the semester. I think we're on pace to make that happen, so we'll see. Okay, so element interconnection laws. So we're on the chapter, the linear graphs chapter, and we started out just kind of introducing the idea of linear graphs, and we did the sign conventions. And we've done quite a few examples kind of as we've gone, but today we'll learn interconnection laws, and then we'll do like kind of put all the pieces together and do some examples too. So it'll be fun. So element interconnection laws. The interconnections among elements constrain across and through variable relationships. The first element interconnection law requires the concept of a contour, which we're going to draw in the text. I will draw with a red dashed line. When we draw them, we can use a dashed line if we want to. Sometimes we get lazy and just draw it continuously because there's a lot of effort that goes into lifting and setting back down your pen as you go around in the loop. So a contour is a closed path that does not self-intersect superimposed over the linear graph. Okay? So it's not comprised of any of the elements of the linear graph. So you draw the linear graph, the branches, the nodes. We're going to superimpose this contour on top of it. Okay? The first interconnection law is called the continuity law. So, get my brush out here. Continuity law states that the sum of the through variables that flow into a contour on a linear graph is 0. Or, in terms of generalized through variables, Fi, for n elements with through variables defined as positive into the contour, if you sum up all of those through variables, you get 0. Okay. Contours can enclose any number of nodes and branches as illustrated in figure 2.5. So let's take a look here at figure 2.5. If we draw our contour just around a node, then this is going to look a whole lot like what? KCL, right? All of the through variables going in have to sum to 0, which in the case of a circuit, all the through variable is current, right? So all the through variables going in, or all the currents going in to the node are summing to 0. So that's KCL. So sometimes, I would say over half the time, most of the time, we're able to just draw these around a node. And we'll talk about when we construct the equations that we'll construct in the next chapter from these linear graphs. We'll talk about which contours to draw. There we'll be very specific about which ones to draw. It'll give us the correct equations that we need. So we'll talk more about that later. But for now, you can draw any contour, and you can construct what's called a continuity equation. So the continuity law gives continuity equations. Okay. So so this first one, we just drew it around this first node, and then we could write a continuity equation, which is the summing up of all of the through variables going into the node, which all of them are leaving this node, right? So the way that it's drawn, the through variable through branch 1, the through variable through branch 2, and the through variable through the source S all are leaving the node. So we said that we're going to define all of them, sum up all of the ones going in. So we have to put a negative sign on all of the ones going out, right? So we have negative F1 minus F2, so that would be F1 is here, right? F1, that's F2, but I don't have space to draw it. And this is Fs. So leaving. So those all have minus signs, and it has to sum up to 0. Okay. Now I don't want to confuse you, but technically we can notice we can multiply both sides of this equation by -1. We would get F1 plus F2 plus F3 equals 0. You can do that too. I just picked 1. I said into the node. You could have chosen plus to be out of the node. Get the same equation. It's fine. Just be consistent with whichever one you do. Okay. It just gets confusing to state something like into or out, but like you gotta choose one, so I thought I would state it more simply. All right, and the second one here, so this node was essentially, the contour was drawn around the node. But now we can draw another contour. Let's draw it around, totally enclosing branch 1, branch 2, and these two nodes. And according to the continuity law, we should be able to do the same thing to it, right? So branch 1 and branch 2 are totally contained within it. They don't cross the boundary. So the only two branches that cross the boundary are the source and branch 3. Therefore, you sum all of the through variables going into the contour, and we have negative Fs, the through variable through the source branch, and negative F3, the through variable through branch 3, because both of them are drawn away from the contour, out of the contour, I should say. So we have negative Fs minus F3 equals 0. This one's not as obvious. So it's pretty obvious to you, and you're pretty comfortable with the KCL idea where you have a node and everything going in has to, you can't store anything in the node, so you have to have it, everything that goes in has to come out. It's less obvious that that has to be true when you totally contain branches within it. But I leave it as an exercise for you to go ahead and write the equation for this node and for this node, and then you can actually eliminate variables to find that Fs plus F3 has to equal 0. Essentially, all of the variables in that are common to the two nodes drop out. F1 and F2 drop out. Okay. So now that we're comfortable with that, we can draw another contour and draw another, and write another continuity equation. So we have branch 1, branch 2, and branch S, the source, all going into the contour. Branch 3 is completely contained within the contour. So if we sum up all of the through variables going in, we have F1, F2, and Fs. All of them are directed into the contour. That has to be equal to 0. Okay? So these are just some of the continuity equations that can be written for this graph. We could draw more contours, I should say. We could get other equations. We have, there are actually maximum unique continuity equations for each graph, but we're not going to be too concerned about defining what the maximum number is of unique ones, because we actually are going, the method that we're going to use to construct well, our state equations is what we'll call them, but our differential equations that govern dynamics, which we did previously in just electronics, the method that we'll use will give us the minimum number that we need, and so we don't need to worry too much about proving number of branches, number of nodes, and how many continuity equations we need. We'll get there in the next chapter. But for now, we know how to write continuity equations that are like this. So we would call this a continuity equation. And we can write multiple continuity equations for one graph. Then every time we draw a contour, we can write a continuity equation for it. Okay. So that's the first. We only have 2 interconnection laws, so 1 for 2. So now we got to move on to the next one. The second interconnection law we consider requires the concept of a loop, which we denote with a closed series of branches, actually, that will do purple or violet. It's called violet, actually. Seriously, it is. So I know I thought violet was not as purple as this, but it's like quite purple. I like the color a lot. So the second interconnection law requires the concept of a loop, which is a continuous series of branches that begin and end at the same node, not reusing any branches. Okay? So we're familiar with a loop from circuits, right? If you start at one node and you go around, you end at the same node that you started at, you have a loop. Now, we've eliminated the possibility of reusing branches in the loop. Technically, the compatibility law we're going to introduce in a second still applies if you have branches repeat, as long as you start and end at the same node. But it's sort of like these trivial cases where you have, like, you'll add in VR3 and then you'll subtract out VR3. So it's really not useful to have reusing of branches, so that's why I keep it to not reusing any branches. The second interconnection law is called the compatibility law. Compatibility law states that the sum of the across variable drops on branches around any closed loop on a linear graph is 0. Or, in terms of generalized across variables, VI, for n elements in a loop, if you sum them up, all of the across variables, you get 0. So this is KVL, right? Yeah, so KVL is a special case of the compatibility law. A loop can be inner or outer, so we can have multiple types of loops. So let's look at this figure here. So it's the same linear graph, but in this case, we're highlighting loops. And it's really hard to see up on the screen, so I'll try to highlight them more. So the graph has multiple loops. There are actually 3 different loops here. So the first loop that we can write, there's no really reason it has to be first, but we're going to choose this one to be first. Branch 1 and branch 2, right? So we'll go branch 1 to 2 if you want. So starting and ending at the same point, there is one loop. The compatibility equation, which is what we call equations that are found from the compatibility law, so compatibility equation. So what we do is we start at a node and we just start going around the loop and counting drops to be positive and gains to be negative. You can actually do it the opposite way. As long as you choose one way, Drops can be negative if you want, and gains can be positive. That's also fine. But I like to do drops positive because it goes in the direction of the arrow. So V1 is positive, and then you have to go against V2 to get back to your original node. So V1 minus V2 equals 0. Second loop we'll consider. We'll start at this node here, and we'll do the compatibility equation at the same time. So follow along here. So we go from this node along V2, and we're going to go in the direction of the arrow and the drop. So we'll say positive V2 plus V3, also in the direction of the drop. And then to get back to the start, we have to go against Vs, which is negative Vs equals 0. Okay? There's one more loop. I think a lot of people missed the outer loop, right? So these first two are inner loops, and then this is an outer loop where you have loops contained within it. It's fine. It doesn't matter that you are on the outside or the inside. It's still a loop. So let's start here again. You can start anywhere, any node, and we'll say positive V1 plus V3 minus Vs equals 0. So those are loops, and they are compatibility equations that are generated below here. Okay, so when you guys draw them, we'll very rarely actually draw in the loops explicitly. I'm just doing this on the graph to show you, but we'll just mostly look at it. Just like in the circuit analysis, we would look at a loop, but we wouldn't necessarily draw in the loop explicitly. Just made our diagram all messy. But you can. If you feel uncomfortable at first, then you can draw them in. That's fine. All right. And of course, KVL is the special case for electronics. Okay. So let's do an example. All right. So for the system shown, so we'll peek at it. Look at that linear graph. That one's cool. I think these can be really pretty. I like them. So, part A, write 3 unique continuity and 3 unique compatibility equations for it. And then part B is to write a continuity equation solved for F4, so the through variable of branch 4, in terms of the through variable of branch S and the through variable of branch 1. Finally, write a compatibility equation solved for V5 so the cross variable of branch 5 in terms of Vs, V3, and V4. So let's do A first. So A. Let me go back to black. So part A, we have to write 3 unique continuity and 3 unique compatibility. So continuity, we'll do first. So continuity requires that we draw contours, right? So when we draw contours on here, we'll do dashed lines just to try to be good about it at first. We want to write 3 unique ones. So a one that's not unique would be one that had the same variables all showing up in it, right? That would clearly not be unique. I mean, there are other ones that could be not unique, but those ones are clearly not. So for instance, we could draw this contour and we could draw this contour, but those both give us the same equations. Actually, since they don't contain anything, they just are both trivial. But In this case, I don't see any other ones that would, oh, so for instance, you could draw this contour. Oh, I didn't dash it. Crap. I could draw this contour. I'm going to draw them solid. It just looks so much better. We're doing them solid. I could draw this contour, or I could draw this contour, and they would give me the same equation because they intersect the same two branches, right? So I'll draw them both. They both intersect S and 5. So they're both going to give me the same exact equation. Yeah?
Is there going to be any other kind of indication when you're looking at the graph that will show you it doesn't matter which one you pick, it's going to equal to each other?
Well, the KV, so this is the continuity equations. There you can write multiple that are the same equation, and same with the compatibility. You can write multiple compatibility equations that are essentially the same, and that's part of why so right now we're just gonna start just writing the equations down. But when we get to the next chapter, we'll systematically decide which of the continuity and which of the compatibility equations we need.
Okay.
So yeah, so there are actually quite a few that you could write, and some of them are redundant, and sometimes it's hard to see that they're redundant. But we're not too worried about that at this point because we're still just trying to figure out how to write them in the first place. But once we understand how to write them, then we'll figure out how to discern which ones to write. But for now, we don't care that much. We're just learning to write them. So continuity, we can choose, kind of like the graph is our oyster right now. Speaking of which, I had an oyster at the gala this Saturday, and I don't know. I feel like I liked it, but it's hard to say for sure. Okay, so it was better than the oyster shooters I had had before, which I do not recommend. Oyster shooters, ugh. Cocktail sauce? Yeah. Anyways, didn't like that. So, if we draw continuity equation, so we can draw a bunch of different contours here, but let's just take one of them. So, like this big one here. Bam. There's a contour, right? So, I'll call this contour Roman numeral lowercase I. So it's 1, right? So I'll do 1, and that one's going to give me what? What's the equation? What's the continuity equation there?
2s equals 3, 5.
Yeah, so it's the through variable of s being equal to the through variable of 5. But let's jumping ahead a little bit and solving it, which we will start doing, but let's slow down a little bit and just say, okay, everything going in is positive, so through variable f5 is going in, right? So that's positive. And then fs is going out, so it is negative, and that has to equal 0. Okay. Let's choose an easy one, the next one. So what is my continuity equation for this contour? 2. Any ideas? F something.
2 variable 2 plus 2 variable 3 minus 3 variable 4 is there?
Yeah. So F2 plus F3, both going in, minus F4 has to equal 0. Okay, the third one, I'm going to give you guys all a chance before I do it to do it. And so I'm going to choose, let's do this node here. So this one will be 3. So give you guys a minute, and I'll come around and help. if you have any questions.
Assassin's Creed. Assassin's Creed. Xbox One use baseball. Xbox One. I don't want baseball. I think that's my final until I graduate. I want to hurry up and see what's on, dude. I think it's done. The one where it's by Little Glass.
Yeah, I'll go in.
That's
Shoot.
true. Oh, God, I'm done.
That
Oh, yeah, I heard great things about it. It's supposed to be a campaign or something. And I'm not really, I don't like
So, you just pick
I
one
don't like
and then you just kind of go along.
multiplayer.
You just complete the circle, you go all
First person.
So you're thinking of the compatibility that should we go around on the branches. When we're talking about continuity
Assassin's Creed.
branches, we're doing on the contour.
Fallout 4 was a
And then we're looking at the ones that come in and out of the contour.
Oh, okay.
So in this case, branch 5, branch 1, and branch 4 all
Fallout 4
in
was
to this contour. So we have
I didn't know Fallout 3 was
F5,
Fallout 4.
Okay.
I like Skyrim. Yeah. I had really good reviews of it. So
We're gonna, alright, if you have any questions.
I was upset. And then I didn't like it. It went through it so quick.
Alright,
I remember it being like,
so I think we're getting there. So
dude,
this contour has 3 branches that go in, right? All 3 of them are going in, the arrows are directed into the contour, and therefore we sum up F5, F1, and F4. So F5 plus F1 plus F4. That has to equal 0. Great. How about compatibility? So what I'm going to do is switch to a different color. Try orange. That should be a good enough contrast on there, I think. So we have to do 3 loops, right? 3 loops in here. And so let's choose this loop to be loop 1. Okay, so if we're gonna write the compatibility equations, so I'll call this loop 1. Then we have to start it, we can start anywhere. So let's start down here. So we start here, we say the cross variable v5, we're dropping in the direction here, so v5 minus v1 plus vs have to equal 0. So v5, we said, minus v1 plus vs has to equal 0. So compatibility, we're thinking about across variables, right? So we went in a loop instead of into and out of a contour, we're going around a loop. And let's have another. Let's do, let's just do this triangle here. So we'll do V3 plus V4 minus V1. So this one's 2. So V3 minus, no wait, plus V4, right? Plus V4 minus V1 equals 0. Okay. And the last one, let's do the entire outer loop here for the last one. So I'll draw it around the entire outer loop. So hopefully it's not too convoluted. All of these.
Does it matter where you start at?
It doesn't matter where you start. So let's start somewhere different this time. Let's start over here.
Depending on where you start, well, it should all give the same answer, though, correct?
Same answer. Yeah, no matter what. And it doesn't matter which direction you go either. As long as you continue along in the same direction, you don't turn around. There's no turnaroundsies, but you can continue. It's just fine. Okay. So let's go this way. So starting at this node, we go negative V2, right? So negative V2, and then plus Vs, and then plus V5, and then minus V4 equals 0. So unfortunately, I cannot write and draw at the same time. So we had negative V2 plus Vs plus V5 and then minus V4 equals 0. Whew. All right, so those were 3 continuity and 3 compatibility equations. And like I said, it'll become our procedure will tell us which ones to write later, but for now we can just write some. Now part B asked us for a very specific one. Okay, in part B, I wanted to know how to write a continuity equation and solve for V4 in terms of Vs and V1. So we just can't see the graph very well now. I'm gonna have to delete these things. You guys have them down though, right?
You said in terms of solve for V4 and in terms of what?
What did I say? In terms of Vs and V1.
Thank you.
Sure. So in terms of Vs and V1, so I want to know V4, which is, F4. F4 in terms of Fs and F1. So I know that, from the experience we've gained so far, if we draw our contour and it intersects a branch, we're gonna use the through variable that goes through that branch, right? So ideally, I'm gonna draw a contour that cuts. So I want V4 in terms of V1 and Vs, right? So I just cut all 3 of them with this. All I need to do is bring this back and close it. I could either go this way or I could go this way. I have the option there. I'm gonna go this way, just for definiteness. So I cut the 3 branches that I want to write the continuity equation in terms of those 3 variables through those branches, right? That was the key. That's why I drew this one. So you could have written like 5 continuity equations and solved for those variables, but instead we're just going to jump to an equation that has just those variables in it. Which is really nice. Which is part of this systematic approach we're going to use is to draw the right contour, write fewer equations, not have to solve as much algebra, which is great. So we want to know, and actually what I'm going to encourage us to start doing, now that we're like experts practically at continuity equations, we're already ready to start this. We're going to say, okay, if I want to know F4, that's what I want to know, right? Then I decide that everything coming out in F4 has to be equal to everything else that goes in, okay? So I can write, and I'll write it up here because I don't think I can fit. Yeah, I can. Okay. So we can immediately, we could just write the continuity equation here, right? Sum up all the stuff going in and solve algebraically. But we can skip a step if we say F4, which is what we want to solve for, comes out of the contour, right? Has to equal everything going into the contour, which in this case, the other things are leaving, right? So we have to give them negative signs, but it's equal to negative F1 minus Fs. Okay, is that clear? I know that that's a little bit of a jump, but we could have easily just said, okay, everything going into the contour is positive, right? We'll just say, and we'll sum them all up. So that means that negative Fs minus F1 minus F4 equals 0, right? And then we could have added F4 to the other side, and we would get the same thing. So if you aren't quite ready to make that leap, it's fine. You can just take one more step and write the intermediate step. Okay, and then similarly for C, I wanted to know what V5 is in terms of Vs, V3, and V4. So I wanted to know what the drop from here to here is in terms of Vs, V3, and V4. So they form a loop, right? So I can write a compatibility equation for it. And once again, I'm going to, so I'll draw in the loop here. So there's this one, this one, and this one. So that's my loop, and I could just write my standard compatibility equation, right? Just go around the loop. Or, which is what I recommend you trying to get to eventually, maybe not today, but eventually, I would recommend doing this. We want to solve for V5. So we want to solve for V5. These work like vector addition, okay? So V5 you can think of as being the vector from this node to this node, right? The arrow is this way. So it goes from this node to this node. It has to be equal to this vector plus this vector plus this vector, right? So you can go around the loop starting at the tail and summing those that drop in the direction you go and subtracting those that are in the opposite direction. So the first one, Vs, is actually in the opposite direction. So you have to do negative Vs. So we're solving for V5. Negative Vs plus V3, because it's going in the direction, it's dropping in the direction we're going from tail to head. So plus V3 plus V4, because it drops also in this direction, plus V4. Whew. All right. Any questions on that? Okay, we're going to start the next lecture because I have a lot to tell you.